In the last session, we saw the meaning of the entropy, and we defined entropy as relative entropy or differential entropy in case of continuous memoryless channel. So using that definition, we'll try to build another parameter in a continuous memoryless channel, which is mutual information, which leads to the definition of channel capacity, which is the actual maximizing the mutual information over certain parameters. Okay, so which will give us which will lead us into meaningful results. Okay, let's say we wish to transmit a symbol. Okay, we wish to transmit a random variable x over a channel. So let us say that x is a random variable which needs to be transmitted over a channel. Okay, so you can say this as a channel, and the receiver receives certain random variable, we call it as y, right? So each value of x from the transmitter, unlike in case of discrete memoryless channel where we considered each of those discrete sample values were represented by each message. However, in case of continuous ranges of random variables, we can assume that the x in a continuous range is now a message. Okay, so the range could be a small the values within certain ranges of random variables. Okay, so we can assume that the message that we are going to transmit would be can be treated as a pulse of height x itself. Okay, so that would constitute that would can be regarded as the message that is transmitted from the transmitter end. The message recovered by the receiver again will be a continuous random variable. Of course, if the channel was noise free, then the received value definitely can uniquely determine what is actually being transmitted by the transmitter end. Okay, so but for since presence of noise, because due to, as it is the case that we are dealt in case of discrete memoryless channel, due to channel noise, okay, it introduces uncertainty. Okay, uncertainty about the true value of x. Value of x which is transmitted. Okay, so let's consider an event where the transmitter is transmitting a value. Okay, say a value transmitting, since it's a continuous range of values, so let's say let's assume that it transmitting a value within an interval, within a range, I can say within an interval x plus delta x. Okay, where delta x is tending to 0 for a very small interval, will pick up one random value, and that random value will assume that is transmitted by the transmitter. Okay, so and hence the amount of information transmitted, therefore or I can say before getting into the amount of information, the probability of this event, the probability of this event, okay, where picking one value within this interval and transmitting over a channel, so probability of this event would be obviously probability of x, which is density function times delta x. So this implies the amount of information transmitted is equal to, by the basic definition of information theory, which is inversely proportional to the logarithmic of the probability itself. Okay, at the receiver end, okay, what's happening here? So at the receiver, the receiver receives a value, a random variable y. Okay, receives a value, say y. Okay, and let's say, and let a conditional probability p of x given y, which represents the conditional probability density of x when y is received. Okay, it's a particular value when y is received. What is the probability density that x was transmitted from the transmitter end? Okay, so and hence we can say that therefore probability of this event, the event here is that probability that x will lie in the interval x plus delta x, okay, when y is received, would be what? Would be the probability density p of x given y times delta x. Therefore the uncertainty or the amount of information which is lost in the channel, so this implies uncertainty due to channel noise. Okay, this probability would have been 0 or unity if there were no noise, like very similar to the discrete memoryless channel argument. So there would be certain there would be an uncertainty involved due to the existence of the noise in the channel. So or the amount of loss of information, okay, that can be written as log 1 over the probability. Okay, so therefore we can quickly write that the net information received, the net information received or the net information transmitted over a lossy channel, that would be represented as, I can say, yeah, I x y, which is the difference of what is transmitted minus the loss of information. So information, I can say the information transmitted minus the loss of information. So this implies the net information received can be written as logarithmic of 1 over p of x times delta x minus logarithmic of 1 over p of x given y delta x, which can be rewritten as I of xy log probability density x given y over probability of x. Okay, so note that this is a mutual information when one certain x is transmitted and when certain particular y is received by the receiver. Okay, so this is true. Okay, as limit delta x tends to 0. Okay, so as this limit as delta x tends to 0, note that this is true for such case, where for smallest interval that is possible. Okay, so but we are interested in finding the average information transmitted over a channel when some random x is transmitted and when some y is received. Okay, so therefore averaging I of xy over all values of x and y. Okay. Let me call this as equation 1 for any future references. Okay, so let me call this as equation number 1. Okay, so averaging over all values of x and y, we would get average information that is transmitted. So therefore average information transmitted will be, okay, this is the average amount of information I of xy I of xy averaging over all x's and all y's. Okay, the joint probability density P of xy times I of xy dx dy. Okay, so which can be substituted using equation 1, minus infinity to infinity P of xy, where we have defined I of xy as a logarithmic of P of x given y probability of x dx dy. Okay, let me call this as equation 2. Okay, and definitely this we have written using equation 1. Okay, then we can still further be simplified this, as since there is log a over b term, we can split that as two terms there. So splitting that as minus infinity to infinity and that as minus infinity to infinity probability of xy times log of 1 over px dx dy plus minus infinity to infinity the joint probability density function P of xy times log of the conditional probability density x given y dx dy. Using a known relation P of x given y, we know that this is probability of x using product rule y given x. So therefore the average amount of information that is transmitted over a noisy channel would be represented as probability of x y given x, right, log of 1 over px dx dy, and this term I can write with a negative sign minus infinity to infinity PDF P of xy, and the minus term can be compensated by taking this into the denominator. Okay. All right. In the first term, if you carefully observe, I can separate the terms involving x, right? So probability of x times log of 1 over px dx can be pulled out, and the another integral, which is the density probability density function, the condition probability density function, probability p of y given x, will be left over, and this I can write it as dy minus, okay, let me retain this as this function, probability of xy log 1 over probability of x given y dx dy. So if you carefully observe, this term is averaging, or its area under the curve of a probability density function, which we know by the property which is unity, okay, by the known property of the conditional probability density itself. And the first term in the product indicates the definition of the entropy itself. Of course, this is relative or differential entropy that we have defined in earlier session. All right. So in the second term, if you carefully observe, in the second term, this term represents, okay, this term represents loss of information, correct, that we have defined earlier in this session. Okay, so that was the uncertainty involved in transmitting transmitting a certain symbol x and receiving certain symbol y. All right, and the product p of x comma y and averaging over all values of x and y. So this complete term is nothing but the average amount of information that is lost due to noise. All right, so and hence we can rewrite this h of the mutual information, or the information that is received by the receiver, or the amount of information that is transmitted over the noisy channel, which can be represented as, so okay, therefore, okay, when some value of x is transmitted, and some value y is received, okay, in that case the average information transmitted over the noisy channel, the average information transmitted over the noisy channel could be I of x y, as the product in the first term is simply the product of h of x times 1, so this is simply h of x minus, as I told, this indicates the average amount of information that is lost, and we can represent that the loss of information averaged over all x and all y as conditional entropy h of x given y. All right, so this is actually it's a similar definition that we have we have done for discrete memoryless channel. Sorry. Okay, so now we can define the channel capacity. So therefore the channel capacity okay, CS is the maximum amount of information by the definition, which is it's a maximum amount of information that can be transmitted. Okay, so this implies CS can be, it's a capacity, channel capacity per symbol. Okay, so transmitted on the average, I can say on the average per symbol. Okay, which can be denoted it as CS, which is the capacity, channel capacity per symbol, is maximum value of the information that is transmitted over the noisy channel. But how to maximize this? So on what parameters that we should be trying to maximize this amount of information that is transmitted? Say, let's, to show that this I of xy is a function of input probability density and channel matrix. Okay, so this I of x comma y, which semicolon y, which we have defined as mathematically as this expression, which has got plenty of variables involved in it. It has got input probability density, it has got the a priori probability density, it also has got the posteriori probabilities as well. So in order to make the function just a variable with respect to input probability density and channel matrix, then we can will be able to maximize this amount of information based on the information of these two quantities. So to make that more clear, let's use some known rules. The joint probability density, which we know can be written as P of x times P of y given x. Okay, let us call a few equations that may be helpful in substituting in the next case. Let me call probably this as equation 3, and we have called one equation as equation 2. All right, so using these equations, okay, and we'll keep this as some equation number 4. Using product rule or using base rule, also we know that probability of x y can also be written as probability density y times probability x given y, which is equivalent to the right hand side probability y given x. So this implies that we can rearrange few terms here. So I can write this as probability of x given y over probability of x, which is equivalent to probability of y given x over probability of y. Okay, so this is a rearrangement is to the fact that we have got a value of or a quantity of probability x given y over probability of x in equation 1 itself. So as you can see, in equation 1 we have a ratio of p of x given y over p of x. Let me try to replace that quantity with p of y given x over p of y, because of the fact that I want to make this I as a function of P of x, which is input probability density, and P of y given x is a priori probability, okay, or we have seen this as the channel matrix as well. Okay, so to make the function to make I of x, y as a function of just based on these two quantities, we are trying to rearrange. Okay, so the numerator is the priori probability. P of y now must be replaced with something else. In the sense, we have to I can write P of y, which is a marginal PDF. We know that this can be written as the joint probability density averaged over all variable x, right? So this can be further be simplified or further be written as probability y given x, and we know that, okay, and we know that from equation 4 we can replace this P of x given x comma y, which is joint probability density, as minus infinity to infinity probability of x times probability of y given x dx. Okay, this is using equation 4, and let me call this equation as, which is actually probability of x given y probability of x given y over probability of x. I have written in this fashion. Alright, so that I can substitute now these 4 and 5, put 4 and 5 in equation probably 2 that we have defined as equation 2. So P of x comma y will be replaced with that product rule, and the ratio we have already calculated, which is in terms of P of y given x and P of x, and hence this can be further be represented as I of xy as minus infinity to infinity minus infinity to infinity probability of x times probability of y given x dx dy minus logarithmic of times logarithmic of probability of y given x divided by x y given x dx dy. Okay, all right. So with that, of course, here there is a term dx. All right, so of course, with respect to input probability density, as well as the knowledge of channel matrix would give me the average amount of information that is transmitted over a noisy channel. Okay, so this implies that I of xy is a function of P of x and P of y given x. Okay, therefore for a given channel, or probably for a known channel, in the sense if we have the information of a priori probabilities, then I x y is just dependent on p of x. For a given PD input probability density function, I can formulate I of x y. So therefore the channel capacity CS now can be written as it's maximizing the average amount of information that is transmitted over the noisy channel for certain PDF. Okay, so this is actually it is per symbol per second. Okay, it's just in a symbol, per symbol I can say. The symbol channel capacity which is actually we can be represented as per symbol. All right. So if the channel transmits k symbols per second, then I can say that the channel capacity it's in general for C as k times CS, which is actually, I can say it's not k symbols, I can say k values per second in other words, because it's not a discrete memoryless channel. Now I cannot say as k amount of symbols, I can say k values. It's a continuous range of values. I can say k values per second. Okay, then I can write C as k times CS bits per second. Okay, very similar to very similar to the case with discrete memoryless channel. Similar to discrete memoryless channel, the mutual information is symmetric. Okay, that can be verified. So which is nothing but the left hand side is h of x minus h of x given y, and the right hand side is h of y minus h of y given x. Okay, so this completes the definition of mutual information using the definition of relative entropy or differential entropy of the source, and hence we try to define the channel capacity. So next session involves the more rigorous treatment or more detailed analysis of finding out channel capacity for a particular channel. The channel would be additive white Gaussian noise channel, which is the simplest of the channel that is possible, since in this case we have not talked anything about the nature of the channel. So if we can we have just said that for a known channel or for a given channel. So let's say that the channel given to us is AWGN, then what could be the capacity of the channel in the events of the channel being band limited and band unlimited. Thank you.